Thanks. So when people talk about technology, they often think about physics and mathematics. So I wanted to talk with you a little bit about how biologists view and mostly viewed mathematics, do a little history tour. So let's start with Darwin. Darwin is famous for not really liking mathematics or knowing mathematics, and he basically said two things about it. So I'm going to talk about both of them. So the first quote is, mathematics in biology is like a scalpel in a carpenter's shop. And this is often simply referred to as indicating that he was innumerate, he didn't like mathematics. That supposedly explains why he didn't read Mendel's paper when it was sent to him. But I think there's more to it, because he chose a very specific analogy. So what's the problem with a scalpel? And I think if you take into account the things that Darwin thought about and cared about, the scalpel is both too precise and too sharp. And why is this a problem for Darwin? Darwin was a naturalist at heart. The fundamental fact about the living world that he emphasized, and that's key for the theory of evolution, is variation. And he thought that mathematics didn't reflect that variation. The second thing that was important for Darwin as a naturalist was interactions between species and so on. In a sense, he was an ecological thinker. And again, you can use a scalpel, especially in the 19th century, to cut through muscles and tendons and so on, destroying the interactions. I think that that's what Darwin meant. A carpenter needs to understand the grain, needs to work with the grain. He has specific tools to work depending on the wood and depending on what you want to do with the wood. So my claim is that mathematics for Darwin destroyed interactions and variations, and I think he was perfectly right for the mathematics of his day. And I want to prove this to you by going to the second thing that Darwin said about mathematics, and that basically exhausts what he said about the topic. In a letter to his cousin, he said, "I have no faith in anything short of actual measurement and the rule of three." So measurement, that's fine. But what's the rule of three? The rule of three is this idea that if you have two ratios, A is to B, a C is to D, you can deduce one number if you have the other three numbers. It's like I don't think people are taught this thing today in elementary school, because now we teach them more complicated stuff. But historically, this was called, at least in Israel, multiplying along the diagonals, kefel va'alachson, and every school kid learned it, as did Darwin for centuries. And Darwin thought, he didn't know a lot of math, he didn't invent mathematics, mathematical ideas, and for him, that was the epitome of mathematics. The problem is that this doesn't work when you have variations and correlations. If you use this sort of A's to B as C's to D to deduce a missing number when various correlations, for example, you have height and you have weight, and you want to say, well, the average height to the average weight is something, let's use this to extrapolate. It doesn't work because height and weight are correlated. This was discovered by Darwin's cousin, Galton, a couple of years after Darwin died. So when Darwin was thinking, mathematics didn't know how to handle variation, which was a very specific reason for why Darwin should have been suspicious of it. So, did anything change? Well, let's continue the story. So now I'm going to jump through several decades in which two things happened in the relationship between mathematics and biology. First is the invention of statistics. We saw the beginning of this with Galton's work, but then we have people like Pearson and Fisher and so on, and some people here know that better than I do, but it is important to realize that the development of statistics was intimately tied to biological and sociological questions. So that's one part of the story, handling data. The other part was trying to use mathematical ideas and ideas from physics to understand the fundamentals of life, understanding why organisms have the shapes that they have, why do they grow the way they grow, using all kinds of metaphors and models from mathematics and physics. The results, to call them disappointing, would be an overstatement. They're kind of ridiculous. And I'm not going to go over them, but if anyone is interested, Evelyn Fox Keller's a book on the topic, Making Sense of Life, where she devotes a chapter to each of these failed attempts is something worth pursuing. It's a very fun book. But I want to jump over these decades and get to where I want to spend most of my time, which is in the 1940s. But first, let's see what was the situation when these people I'm going to talk about started working. So in 1934, there was a very important meeting in Cold Spring Harbor Lab, the second ever Symposium on Quantitative Biology, which became a very famous series of lectures, but it was the second one. And the topic was growth. And the beginning of the invitation says, well, growth, it's such a complicated topic, we need multidisciplinary approaches. We need mathematicians and biologists to work together. Some people declined to come, I guess, and some people sent in their contributions. Apparently they didn't want to come. One of them was E.B. Wilson, who was one of the most important biologists of a period at Harvard. And the title of his talk, which was just sent in, is Mathematics of Growth. And it starts by listing these 5 axioms, or platitudes as he calls them, about the relationship between science and mathematics. And he started saying science need not be mathematical. So he says what we biologists do by observing, building taxonomies and so on, it's science, even though maybe physicists don't think it is. And the second is, simply because the subject is mathematical, it need not therefore be scientific. And here, think about the types of projects Evelyn Fox-Keller writes about, which is people saying we can understand the shape of cells using these simplified equations from physics. Some of these people were other contributors to the same meeting. So we can see here that he's voicing this very, very deep-seated skepticism. However, after explaining why this doesn't work, he ends up by saying, well, one must not fail to mention, as contrasted with empirical curve plotting analysis, what we would now call overfitting, right? The attempts at fundamental rational analysis. Well, maybe they can do something, though the jury is out because thus far they didn't contribute a lot. Which brings me to the 1940s. And to these two gentlemen who were probably the most famous mathematicians of their time, and among, I guess, the top 10 ever. If some of you don't recognize them, we have here John von Neumann and Norbert Wiener. During the 1940s, both of them became preoccupied with biology for various reasons that I assume you know or can guess easily. Together, they were among the co-conspirators urging these Macy conferences that were mentioned here, and they also detested one another, and their interaction is kind of a fun thing to behold, but I'm not going to get into all these sort of details. I want to talk about the way they approached biological questions, because they did it in remarkably different ways. Let's start with von Neumann. Von Neumann, who is typically considered someone who made some contribution into how mathematics and biology work together, which I'm going to dispute. So he first was interested in the brain because he was interested in computers. But because he was a smart dude, after a very short time, he realized that we don't know enough about the brain. So he said trying to understand the brain using the tools we have now is like trying to understand the ENIAC, one of the earliest computers, with a fire hose. So he decided to do something else instead. And he thought, well, let's find something reductionistic, minimalistic, right? So he decided to explore self-replication. And self-replication at the time, many people thought it was a paradox, a contradiction in terms. If a system builds another system, the new one has to be less complex. So self-replication is impossible, hence vitalism or what have you. So von Neumann, who was a great mathematician, proved that you can do this. So he has this nice little proof, but nobody paid attention. So he started developing these more concrete models. They're not concrete in the sense that you have them in the lab. They're all on paper or in your mind, but they're more concrete. They're not just a proof. And the most famous one was the cellular automaton, which he invented. That's the origin of what's the game of life and all that sort of thing that many of you know. And he proved that inside it he can embed a self-replicating system. I'm not going to explain it, but this image is iconic. You find it reproduced in many, many places. I think that's most self-reproduction that we have with this thing is the image that he designed. It's kind of amusing that he never completed the design, but it was concrete enough for people to suddenly accept the idea. This work is often referred to as something that had great impact. People, Langton, when he writes about artificial life, says, well, this is the beginning of artificial life. People who did all kinds of more fine-grained work on self-replication, of course, cite this as the beginning. Cellular automata are used as models for phenomena unrelated to self-replication, so of course everybody mentions this work. But did it really have any influence on how biologists study self-replication? Well, remember, this was before DNA, so you'd think it had any impact on understanding DNA and how DNA replicates. It didn't, right? So in retrospect, people say, look, he, in some distinctions you have here, reflects things about DNA, but that's hindsight. It didn't have any impact. You want to see people working in biology citing this and using this, you don't find anything. The one thing that you do find in 1958 in a biological journal, but it's not a biological paper, in the Annals of Human Genetics, we have this somewhat amusing or entertaining or perhaps inspiring work by Lionel Penrose, who is Roger Penrose's father, who was a geneticist, giving this sort of plywood model of self-replication. So he has these two types of hooks that you see here, and they can hook up either this direction or this direction, depending on the hooks. And if you have like a whole bunch of them, like on a little tray, and you kind of shake the tray, sometimes they hook up together, sometimes they don't. But what was nice is that he managed to build it like this, that if you start with one pair that is hooked in this direction, when you shake it, all the others hook up in this direction. If they are hooked in the reverse direction, when you shake the tray, everything is hooked in the opposite direction, right? So he said, look, this is just like von Neumann, but it's more concrete, it's from plywood, yay. And then he ends up saying, does this tell us anything about biology? He said, well, maybe it tells us something about the backbone of DNA. At this point, we know the structure of DNA, right? So he says, well, maybe the sugar backbone, maybe it's something like these hooks. He says, the jury's out, we still don't know. Well, it doesn't. So this work that's typically, especially if, like me, you grow up in computer science, if you talk to mathematicians and computer scientists, this was like important work, highly inspiring, not really, in my opinion, in biology. Now what happened with Norbert Wiener? The story of the reputation of his work is the opposite. So Wiener worked on self-guided anti-aircraft guns during the war, where he used negative feedback, which the idea didn't originate from him. Negative feedback was known to engineers. But working on it, he realized that if you don't build your system correctly, and you get a system that instead of honing in on where it's supposed to go, like the oscillations go smaller and smaller, they become larger and larger. He said, well, this is cool. He said, well, this is kind of like a bug in a system built using negative feedback. Well, maybe some human pathologies are like that, right? So he went to his colleagues in Harvard Medical School and said, well, does something like this happen? And they said, yes. There is this phenomena called intention tremors, where people, when you ask them to touch their nose, instead of getting like the tremors getting smaller and hitting the nose, they just grow bigger and bigger, larger and larger. And if you Google it, you'll find YouTubes of this. It's quite remarkable. And I said, well, what's the etiology of this? Well, it's a problem in the cerebellum. He said, well, maybe the cerebellum, its job is to handle negative feedback. Well, that's kind of a leap, and as far as I know, this didn't end up being a research program. But what Wiener suggested next, with two of his colleagues, one of them an electrical engineer and one of them a physiologist, and I think that's a key difference from von Neumann. This was an interdisciplinary team from the beginning. They suggested, in a philosophy of science journal, no less, that this idea of negative feedback is the core idea behind purposeful behavior, goal-driven behavior, teleology, what have you. And they have this not very a visually appealing image that nobody repeats about this classification that they give. So typically when this work is presented, it's kind of like philosophers found all kinds of problems in their argument, which are right. Biologists learned that cybernetics was a failed research program, so people always mention cybernetics, in parentheses, that nothing didn't go anywhere. But if we look more carefully, what happened is more complicated. But before getting to this, I want to hint why von Neumann is considered the way mathematicians should approach biology, even though it was a dead end. And Wiener, who I'm going to tell you did influence the entire way we think about the living world, is considered a failure. And I had various ideas about this, and then I read the classification of mathematicians given by Giancarlo Rota, who was a philosopher but mostly a mathematician. So, he has the credentials to say how mathematicians think. So he said there are two kinds of mathematicians: the problem solver and the theorizer. The problem solver is what we typically think of as a mathematician. He gets a puzzle, he solves it, he proves the results, and he moves on. He doesn't care if the result is not very elegant, but it's proven. He can move on. The theorizer is mostly concerned with definitions. He tries to hone in the definitions. And typically, what happens is that at some point people say, well, your definitions are trivial. We can start using them and forget about the theorizer, right? As Rota says, the moment of glory comes from the discovery of a new theory that does not solve any of the old problems but renders them irrelevant. So, of course, mathematicians look at this and say, you didn't solve any of the old problems, right? So Wiener, in this work, both of them did the two kinds of work, and both of them, when thinking about biology, used both approaches. But in the stories I told you, von Neumann was the typical problem solver. He, at the same time, invented game theory and managed the Atomic Energy Commission. He just went from thing to thing. He solved the problems and went on. He worked for Los Alamos, but of course he didn't reside there. He just came on weekends, right, to solve the problems. And Wiener started with this concrete thing, and then he overgeneralized to this theory and conceptual toolkit. So of course, for mathematicians, you celebrate von Neumann, you denigrate Wiener. Before seeing if Wiener did indeed win the day, as I'm going to suggest, let's see if after these two great mathematicians tried to influence biology, biologists were convinced. Suddenly, yay, we like mathematics. So no, they remained as unconvinced as was E.B. Wilson and Darwin. So this is Dobzhansky, one of the most important and celebrated geneticists of the 20th century, in 1951. So he said, experience has shown that, at least in biology, generalization and integration can best be made by scientists who are also fact gatherers rather than by specialists in biological speculation. And the way I read this is people doing biological theory, doing mathematical biology, or in short, mathematicians. That's how I read this. And this is like, we are fact gatherers, biology is an empirical science, we're interested in variation. By the way, Dobzhansky's great research project for many, many years was variation. In this sense, he is very close to Darwin because of various Russian influences, by the way. So it's a complicated story, but in a period in time in which biologists tended to forget about variation, Dobzhansky cared about variation, which I'm suggesting to you is why he also distrusted these clean solutions. And just to show you that it's not just evolutionists, this is a quote from John Eccles, who was a neurobiologist and Nobel laureate, and after seeing von Neumann's self-replicating automata, he said, one may doubt if von Neumann expects us seriously to accept this logical game, which is but a mere caricature of reproduction, for it involves a tacit assumption of a supervising genius, who not only designs automata and has blueprints of them, but also initially inserts instructions into them, so that in principle they would go through the motions of a reproductive cycle. Basically he says, are you kidding me? Is this supposed to be serious? He doesn't even engage more than that, because it's a joke for him. But a decade and a half or something like that later, Jacob and Monod discovered the Lac operon. And the Lac operon, which is the basic unit or the basic idea or conceptualization about how gene regulation works, depends, and in the interest of time, I'm going to elaborate on this, but it's based on negative feedback and negative control. So there's both negative control because it's based on a repressor, And once the gene is starting to be expressed, there is negative feedback to stop it when it's no longer needed. And Jacob talks explicitly about cybernetic systems when he talks about this. And biologists tend to think, all their examples are with negative feedback. During the last 2 days, we've seen these slides, how you help Parkinson's patients. So you have like this diagram of all kinds of things. You don't understand them, but some of them have arrows, and some of them have arrows that instead of having an arrowhead, there's like a little ball, because that's inhibition, and that's negative control. And this is why, Professor Ahmedi, who's not here anymore, I said, I'm not going to explain this, but you bump this, then suddenly it works. The way it works is that you have a repressor of a repressor, and an inhibition of an inhibition. So if you stop one of them, you suddenly inhibit something. All these ideas are directly related to Wiener's work and emphasis on negative feedback. And the influence is perhaps only becoming more and more pronounced and realized by biologists. So this book from Sean Carroll, it's from this year, from 2016, the Serengeti rules. He says, well, it's the same rules underlying the microscopic world of molecules, gene regulation, cancer, and ecology. All of them are similar. And if we understand regulation, we'll be able to understand them better, intervene when we need to intervene, not get disasters when we intervene because we don't realize how the system works. And you read the book and you say, well, where are these rules? And it's negative feedback again, negative feedback again, and negative feedback again. So this uninspiring work, which was basically a dead end, and it led to these conferences where people talked to one another and nothing came of them, which that's what the people at the time thought. It's not just their reputation, right? If you read the concluding meeting, it's like, we didn't learn anything. We just learned how to argue with one another. That's what they say. Well, it did influence biology. So what can we take from this to the future? So another Nobel-winning biologist, Sidney Brenner, said the problem of biology is not to stand aghast at the complexity, but to conquer it. And there are two approaches to conquering: the scalpel and the carpenter's toolbox. That's what I'm suggesting. And we know what Darwin would have chosen, right? He said, you don't need the scalpel. And I think that's exactly right. That's what at least the history shows. And what do I mean by that? I think that one thing that was key to cybernetics, not in the Macy conferences, but more in the British tradition, but this distinction many of you know better than I do, involved tinkering. Tinkering is where basically Wiener discovered the importance of negative control. Remember these tremors? The tremors was because of playing with his systems. Yeah, after that, he wrote down the differential equations. He was a fairly competent mathematician. That's, of course, an understatement. He was a great mathematician. But tinkering was key. And here he is, no more a caricature, a human being, with a contraption. He's tinkering. So I think we need less scalpels and more carpenter-like work. But notice that he did a specific kind of carpentry. He used carpentry to sharpen and develop and cut, whatever metaphor you want, concepts. What biology really needs, that's me on my high horse, is better concepts for understanding its phenomena. And designing concepts is very hard. You can do it with a scalpel, and then you come up with these things that are very elegant, but typically, or at least in the example I presented, tend to be a dead end. Or you can tinker, come up with concepts that have flaws, but that can lead to greater work. And I think this is a very different mode of intellectual production than mathematicians typically have in mind. So what do we need? First of all, we need people that are interested in concepts. And mathematicians are interested in concepts, but we philosophers are more. So I think it's not a coincidence that Wiener's paper was published in a philosophy of science journal. But we philosophers need to understand that this philosophy needs to be done hand in hand with tinkering. And I think tinkering is really nice because people say that evolution is a tinkerer. So for me, it's a badge of honor. But so if the artists in the room and so on, people working in maker spaces and so on are offended when I say that they're tinkering, I say it with for me that's a badge of honor. I think any conceptual biology lab needs to attach to it a makerspace in a sense. So one thing is tinkering. The other thing is we need to pay attention to what people that are working in experimental evolution are doing. And I find it kind of surprising that in these 2 days we didn't talk about experimental evolution. Some people in Israel are doing very, very cool work in this. But the important part of it is not always what they think they are after, but the unintended things that they're going to discover. Another area is what people are doing with robotics, not because robots are mediators and all of that, not that this is unimportant for from other perspectives, but from my perspective, people that work with robots, because they're tangible, because they're typically not alone, they have these social swarming systems, they notice phenomena and they cannot ignore some phenomena that have very clear analogs in the living world, even if, of course, this is an analogy, which is then used to develop concepts. Like I said, I don't think the idea is to transfer results. The idea is to transfer intuitions. And the same thing goes to synthetic biology. The problem with synthetic biology is if you don't understand what to take out from the work being done. So if we consider this work of Craig Venter, I didn't plan on talking about it, but it was mentioned a few times already. If you try to build a cell, a minimal number of genes, and you realize that there are like 500 genes that you have to put in there, which you don't know what they're there for, but you can't take them out because you can't figure out why, right? It's not that okay, I discovered a new gene. They don't know what they are, but if you don't have these, I think it was like 479, but like I said, I didn't plan on talking about this, so I didn't check. And then you have to put it inside an existing shell of a cell, because that part the genes don't do by themselves. So what we learn from this is both what you can achieve via the genome, which is cool, but also what you cannot. And the idea is, how can we then theorize about this? How can we think about this? So I think in this respect, the relationship I see between biology and technology is as two hotbeds. And I think it's interesting that when mathematicians approach these questions and when physicists approach these questions, even though they can combine the type of top-down work of someone like von Neumann and the bottom-up approach of someone like Wiener, they typically don't. They typically either gravitate toward one approach or the other. But we shouldn't accept this as one of them when they represent their approaches, this being the only one, because that's wrong, nor that these are mutually exclusive. And I think here, the type of projects and ideas that were floating around the last 2 days are in fact, in a much deeper sense, a way forward in intellectual production. Thanks.